Assalamu alaikum wa rahmatullahi wa barakatuh. So, in the last few lectures, we discussed about the filters. So, today we will start a new topic, which is nothing but the oscillator. So, we will discuss oscillators. Okay. So, what do you mean by oscillator? Okay. So, it is a circuit. Basically, it is a circuit. It is a circuit which produces or that produces a periodic waveform. For example, you can see that suppose you have a oscillator. For example, you have an oscillator. Okay, you don't need to produce, you don't need to give any input. You just need to give a DC power supply. Then it will produce you the oscillations. And these oscillation can be anything. It can be, sometimes it can be sinusoidal wave according to your design. It can be, sometimes it can be, you can also produce the square wave. Okay, so you can also produce square wave, or you can have an output like a sawtooth wave. Okay, like this. It's not like this, sorry, sawtooth wave. Okay, you can have a sawtooth wave like this. This is the sawtooth wave. Okay, so this is actually the square wave. You see, square wave and sinusoidal wave, then the sawtooth wave. Okay, all these are actually nothing but their periodic waveforms. So this kind of periodic waveforms are produced by using oscillators. So if you need to produce periodic waveforms, if you need to produce the periodic waveform, then you need what? You need oscillator. Okay, so oscillators are the circuits which are used to produce the periodic waveform. Now we can classify the mainly we can classify the oscillators into two types. That is, one type is nothing but the feedback oscillators, and another one is nothing but the relaxation oscillators. And the special thing about the feedback oscillators are actually it will use a feedback circuit. Okay, and these feedback circuits may sometimes, it contains R resistor, maybe sometimes capacitor and inductor. Okay, and these are all the feedback oscillator, and usually it contains an amplifier. That amplifier can be made using operational amplifier, or by using Jfet, or by using the transistors like your common emitter, common drain, all these things, common source amplifier, etc. Okay, so it contains an amplifier and a feedback network. Okay, that's what I am saying. And this feedback network may contains R, L or C elements. Okay, and this feedback network may contains R, L or C elements. So it contains amplifier and a feedback. And usually the feedback type, the type of feedback used is positive feedback. You see here, now we are using positive feedback. So as far as a simple amplifier is concerned, we were using the negative feedback. Now we are using positive feedback in oscillators. This is the use of positive, one of the use of positive feedback. Now what about the relaxation oscillator? This relaxation oscillator, which usually contains an RC network plus a device. This device having some property, actually, plus a device which may which may change the state, which may change the state according to its input. Okay. So relaxation oscillators are the oscillators which may contain an RC network, and it may contain a device which may change its state. For example, you know that a comparator, for example a comparator, if you have a comparator, that comparator will change the state according to the reference voltage that you are giving. So those kind of devices, for example, you may have a comparator, maybe you may need an RC network, and you may connect it together in a special configuration, and according to the voltage across the capacitor in the RC network, the comparator will change its state. So this kind of arrangement is used in relaxation oscillator. And in feedback oscillator, we will use an amplifier and a feedback network. And the type of feedback that we use in the feedback oscillator is the positive feedback. This is very, very important. So these are all the classification of the oscillators: feedback oscillator and relaxation oscillator. So first of all, we will be discussing some more details about the feedback oscillator, and we will see some types of feedback oscillator. After that only we will see the relaxation oscillator. So feedback oscillators, feedback oscillators. Okay, feedback oscillators. So in feedback oscillators, I told you that we need an amplifier. We need an amplifier. This is an amplifier. Okay, I am just using the notation of amplifier, not operational amplifier. I am just using the amplifier, and we need a power supply. This power supply we may call the bias or the VCC. This is a DC power supply, DC power supply. Okay, and we have the output here, we have the input here. Okay, but we have no other input except we will take some part of the output and we will pass it through a special kind of network, and that is the feedback circuit. Okay, feedback circuit, feedback circuit with some attenuation. It is having some attenuation. Okay, we know that what is attenuation? Attenuation is usually represented as B, right? Like this. So we have some attenuation here, and we have some phase shift here, phase shift, some phase shift here, and we will connect this output again to the input of the amplifier. So what I want to tell you is that how this is working actually. So when you switch on the power supply, for example, you have a power supply here anyway. So this is your switch. When you turn on the switch, this is a switch. When you turn on the switch, there will be some disturbances in the circuit. Okay, this may be due to the thermal noise, maybe due to some noise, thermal noise, or maybe thermal noise due to the resistors in the circuit. In the circuit, there will be resistors or resistances. So due to this resistance may produce sometimes the thermal noise due to the temperature. Some disturbances will be coming into play. So because of that, some small output will be available. Okay, and this output will be reaching here at the feedback network. Then it will be here, it will reach here, and this output may reach here at the amplifier stage, and this amplifier will amplify this again in the second stage. The amplifier will be amplifying in the second time, and this will reach here, or I will write it here itself. Okay, it will reach here, then it will be reaching here. So again it will reach at the input of the amplifier, then the amplifier will again amplify this. Okay, so what is happening here? Due to this small disturbance, what is happening to the small disturbance? The small disturbance is fed back by feedback network. After that, it will get amplified, then amplified, then amplified. It will go on. That means some oscillation is starting actually. But there is a problem with this. You can see that it is exponentially, it is increasing exponentially. So we need some control mechanism for the controlling it. Anyway, that we will discuss later now. Okay, we will discuss later. So this is the basic structure of the oscillator. That is, it contains an amplifier and a feedback circuit with some attenuation and a phase shift. But there is a problem here. You see, what should be the total gain of total phase shift of the system. So we are going to discuss about the total phase shift of the system. Now we are going to discuss about the total phase shift of the system. Suppose we are using an amplifier, we are using a non-inverting amplifier. If we are using a non-inverting amplifier, then if we use a non-inverting amplifier in an oscillator, then what is the situation? That's what we are going to discuss. So we have an amplifier, so, and this is our feedback network. This is our feedback network, and we connect the output of the feedback network to the input of the amplifier, and we have some DC power source, DC power supply, DC power, or this, and this is the output. Okay, and now we are expecting some oscillations at the output. So we want to produce the oscillation. So what is the condition for this oscillation? Okay, now you know that suppose you have a feedback network. Your feedback network is producing some output, suppose something like this. As I have told in the previous part that when you turn on the switch, there will be some disturbances and it will get amplified and amplified and amplified, and finally at the output you will be getting a waveform like this. So suppose at the initial stage you turn on the power supply. Okay, you turn on the power supply, let's say, okay, you turn on the power supply. This is a switch here, this is a switch. You turn on the power supply. If you turn on the power supply, what will happen, that it will produce some output here. Okay, and this will be reaching here at the attenuation, and your feedback, it will be giving here like this. Sorry, it will be just little bit diminishing, it will be attenuating anyway. So you are getting something here, and you are again having the same input here something, and at the next stage your amplifier will amplify your input, so you will be getting something more. So this become large, so this also become little bit large, and again you will get something here, and you will get here something very large. At the third state I will use the color red color. Okay, so this is increasing, but you see here that both all this signal at the input of the amplifier and this are at the same phase, because the phase difference, you see the phase difference is 0 degrees. That means both are at the same phase, you see, both are at the same phase. That means if this is positive, you can see that the output is positive. If this is positive, you can see that the output is positive here. Okay, so like this, this one is not here, you can see that this output is positive. So both are at the same phase, and also you see at the feedback network, this is the input and this is the output for the feedback network. So this is the input for the feedback network and this is the output for the feedback network. Whenever the input is positive, the output is also positive. When the input is negative, the output is also negative. Similarly here also at the second stage, that is positive, you are getting positive. When you give the negative, you are getting the negative. So this is what happening, all are at the same phase. So the phase difference here, it is also 0 degrees. Understood? That means there is no phase change. Both are actually in phase. So this is also in phase, and this is also the same phase, or you can say in phase. So we need this kind of condition. So if I take the total loop of the system, if I take the loop, complete loop, the total loop, actually, if I take the total loop, so the feedback actually I can give it as B. So if I take the total loop, the complete loop, the complete loop or closed loop, the phase shift is 0 degrees. If the phase shift is not 0 degrees, then this kind of condition is not possible. That means you cannot get the oscillation. If you see here that if you take something like this, suppose you have a amplifier, if you are giving the input here, then you are getting just opposite. That means positive negative is giving you negative positive. If this is the condition, then you have a feedback network. Suppose you have a feedback network, B is the feedback network, and this feedback network is in phase. So this is like 180 degree out of phase, and this is you are giving something here minus and plus, then here also you are getting minus plus, for example. That means here the phase difference is 0 degree. Then you see these two signals are not same, so it will lose that continuity. So one time it is like positive, another time it is like negative. That means this circuit, this will not work. So you need the total phase shift as 0 degree, or I can say it should be 360 degree, or the multiples of 360 degree we can say. So the total phase shift should be 0 degree. So what I am saying is that if I am using a non-inverting amplifier, then the phase shift should be 0 degree or 360 degree. What I am saying 0 degree, for example. So the amplifier is here, this amplifier is here, and this is your feedback network, and you are connecting here, and there is a DC power supply, and this is the V out. If you give a voltage here, you will get the same phase, and here if you give something here, and you will be getting the same phase. That means positive will give you positive and negative will give you negative. Positive will give you positive here, and negative will give you negative. So this kind of thing is happening in non-inverting, if you are using a non-inverting amplifier in a oscillator. Okay, so you need a phase shift. Phase shift should be, that means the total closed loop total phase shift should be 0 degrees, or we can say 360 degrees. Why I am saying 360 degrees? I can use the inverting amplifier also. That means if I am using inverting amplifier based oscillator, then in that case I have an amplifier which is this, and this is an inverting amplifier. I have a power supply here, DC power source, and I have a feedback network B, but this feedback network should have some special properties, and this is your V out. So I am giving a signal here. Suppose I am not giving any signal, it will automatically generated due to the thermal noise. So you see here that this, suppose this is positive, this is negative. Your amplifier should give, in inverting configuration, your amplifier will give something like this. If you give positive and negative, you will get negative and positive, negative and positive. So you are getting here negative and positive. So you need the same signal here, here and here. So your feedback network should give something like, same signal means same phase. Okay, I am not saying about the amplitude now. So your feedback network plus minus. So what has happened? Your amplifier actually multiplied your signal. If you give a positive signal, your amplifier is giving you negative, and your feedback network at the input side of the feedback network, actually here you are getting negative, and then it should be positive. Then only both are at the same phase. This is showing same phase. So if the amplifier is having a gain which is negative, then your B also should have a negative gain. That means that this negative is showing it is 180 degree out of phase, and this negative is showing again 180 degree out of phase. So this is amplifier is giving 180 degree, and your feedback network is also giving 180 degree. So the total phase shift is equal to 360 degree. So this is the condition which is required. Okay. Now we will see. Now we have seen that the first condition for the oscillation, we have seen that the first condition for the oscillation is that the total phase shift should be equal to 0, right? Or I can say the 360 degree, integer multiple of 360 degree we can say. Okay. Now there is another issue. There is another issue also. Suppose you have an amplifier. This is an amplifier and this is a feedback network. B, I am saying it's a feedback network. So this is a feedback structure of the feedback oscillator and this is a V out. But I told you this is your DC power supply and there is a switch. When you turn on the switch, due to that disturbance, maybe some small signals will be generated. Okay. And what that small signal may be a noise. It is not a sinusoidal wave. It is not a sinusoidal wave. So it contains many frequencies. As I have told in the filters, that filter is used to filter out some particular amount of frequencies. So it contains many frequencies. But I am interested in only one frequency. That means I need only one frequency. Let's say FR. This is my resonant frequency or my frequency of interest. So what I will do, you see here that if I set my gain of this amplifier, for example, my gain of this amplifier is, let's say this gain is AV and this is beta, then the total closed loop, total gain actually of the loop is, the loop gain will be AV into beta. Suppose we have three conditions now. Suppose we can have three conditions. The first condition is that AV into beta is greater than 1. Then AV into beta is equal to 1 and AV into beta or B is less than 1. So we have three conditions. We will check what will happen if we set the gain AV into beta of the total loop. For example, I assume that I will use the next page. So this is your AV and this is your B or beta, we can say. This is V out. Suppose you have the gain AV is equal to 3 and you have the B is equal to 1 by 2. Then this means that AV into B is equal to 3 into 1 by 2, which is 3 by 2. It is 1.5 and 1.5 is greater than 1. So this condition is showing AV into B is greater than 1. Okay. That means your attenuation is 1 by 2. I am saying the attenuation is 1 by 2 and the gain is 3. That means that this I am talking about the condition AV into B is greater than 1. Now what will happen in this case? Now when you have a this is your amplifier. I will show like this. Okay, this is AV is equal to 3 and you have a DC power source. When you turn on the switch of the DC power source, some noise will come into picture and because of that noise you will have some output like this. This is a noise output and this output actually it will reach here and also it will be reaching here. So this output you will get it here, but this network initially it is a frequency selective network. Anyway, this is a frequency selective network as like your band pass filter. It is having a band pass filter behavior. That means that it will allow only some particular range of frequency. Let's say this is FR and this at FR the maximum gain of this network is 1 by 2. As I have told here, this is your 1 by 2. So the maximum gain is 1 by 2. So many frequencies are coming here, and all other frequencies actually will get blocked, and it will select only mainly your FR frequency. So at the output you will be having FR. This FR will be the output, the frequency, the signal with the frequency FR will be at the output, and that will be reaching here at the amplifier. Now what will happen, the gain of the amplifier is now, it is equal to 3. So it will amplify 3 times. So your signal become large, actually it will become large. Okay, I will use it here, I will draw it here. So your signal will become 3 times amplified, your signal become 3 times amplified. Okay, now you got a large signal here, so this is now 3 times amplified, actually multiplied with 3 you are getting. Now what will happen, this signal, your signal will be reaching here, and it will be reduced to half. Reduced to half means what, its amplitude become will be reduced 1 by 2 by a term 1 by 2. So a half of that signal will be reaching here. So the output will be 1 by 2 times, this is 1 by 2 times the signal at a frequency FR. Now this signal is reaching here. What will happen? It will be multiplied again 3 times. So the signal will be increasing again. Now in the next cycle this is going to repeat. So the signal will be again increasing. That means that what is happening to the output, your V out will be looking like this. Your V out will be looking like this. Initially it was small, then increase. It is going very large value, and finally your operational amplifiers that you are using in the oscillator will get saturated, and finally your output will be saturating. I will draw that anyway. This is happening. Suppose this is the point of saturation. So whenever it reaches that points, the op amps get saturated. Yes, saturated. It's clipping here, clipping here. So this is what happening to the output when your gain AV into beta is greater than 1. So this is a problem actually. So no longer now at these points it is not sinusoidal, but here it is okay. Okay, it is exponentially growing sinusoid, but here it is not sinusoid. So this cannot be used. Now what will happen, your AV into B is equal to 1. So if AV into B is equal to 1, the second case AV into B is equal to 1. Now you can imagine AV into B is equal to 1 means that if you have an amplifier, let's say the gain is equal to 3, then your B is equal to 1 by 3 at some particular frequency FR. Then it will be feeded back and you will be getting the output, and you have a DC power supply. So when you turn on the switch, you have a very small signal. Again, that signal will be reaching here. So it will become 1 by 3 of that signal here at the output. Then that will be reaching here. You will be getting the same signal. So what will happen? Then this same signal will reach here. You will get the same kind of signal here also, and again its amplitude will be same. So what I am going to say is that all these amplitudes are same. That means that whenever the oscillations start, you have some amplitude due to the thermal noise. That amplitude will remain as such. It will not increase or it will not decrease. So whatever amplitude, maybe this may be in the order of microvolts. That's a problem. So you will not see any output. So this is not a good circuit. So we have seen that this condition is not good here, and this condition also always it is not good. Now we will see what will happen if AV into B, if AV into B is less than 1. If AV into B is less than 1, as I told you, this is your AV and this is your B. Suppose it is less than 1, that means that suppose this is equal to 3 and this is equal to 1 by 4, then AV into B is equal to, the gain is 3 and this attenuation is 1 by 4, it is 3 by 4 which is less than 1. This is an example. Okay. So this kind of scenario, then initially you have some oscillation, but the oscillation will die out. This is what happening. So the oscillation will exponentially decrease, and finally you cannot see anything. So this is also not good. So what we need actually, that's what we are going to discuss now. So what we need a particular condition, that we have an amplifier AV and we have an attenuation or the feedback network B, which is frequency selective network, and this is your V out. Now our output actually should be steady oscillations. It should be like this, right? We need steady oscillations at the output. This is the output we need. Sorry, okay, this is my output. But initially actually, so at these points what I need actually, at these points my gain should not change. That means total gain AV into B should be equal to 1. If AV into B is equal to 1 at the final stage, this is the like final stage, final output, right? So at the final stage actually AV into B should be 1. But at initially we have only very small voltage due to the thermal noise. So we need to amplify that voltage. So for that we need something like this. Our oscillation should increase like this. So at this point you see the exponential increase is there. So initially we need AV into B greater than 1. So after some point onwards actually we need AV into B equal to 1. So this should be our V out. That means that initially we need AV into B greater than 1, then later on after reaching the required amplitude for oscillation we need AV into B is equal to 1. So initial point actually we need this condition, and at the final stage actually we need AV into B is equal to 1. So this can be done by using some particular type of arrangement. So at the steady state we need actually what, AV into B should be equal to 1. So I am going to conclude mainly 2 points: the conditions for oscillations, The first condition that we have studied was the total phase shift around the feedback loop must be 0. Okay. or maybe integer multiple of 360 degrees. And the second part actually that we have seen now is that the initially we need AV into B greater than 1, and at steady state, that's the main thing, at steady state we need AV into B is equal to 1. So this is main point, okay, this is the main point, okay, and this is another main point. So these are all the 2 points, okay. That means the total phase shift is equal to 1 and AV into B is equal to 1. Sorry, total phase shift is equal to 0 and AV into B is equal to 1. So these are all the very, very important points which are the conditions for oscillations, okay. So these are all the conditions for oscillations. I hope this is clear to you, okay. Now we will see different types of oscillators. What are the different types of oscillators in feedback, well, different types of feedback oscillators. So different types of feedback oscillators. So the first one is the Wien bridge oscillator. It's the name of the scientist and all. So Wien bridge oscillator, and it uses RC network in the feedback. So RC feedback network. So it uses RC feedback network. Now the second type is the phase shift oscillators. Phase shift oscillator, and it also uses RC feedback, okay, RC feedback network. And the third one is the twin T oscillator, and it uses also RC feedback network, okay. Then the fourth one is the Colpitts oscillator. It uses LC, inductor and the capacitor, okay, feedback. Now the fifth one is the clap oscillator, and it uses LC feedback network, okay, as a frequency selective network. And now it's sixth one. Then the Hartley oscillator, and it also uses LC feedback network. Then seventh one is the Armstrong oscillator, and it is the LC feedback network. Now due to the time limitation, we will be discussing about the Wien bridge oscillator. We will discuss about the Wien bridge oscillator, and we will discuss about the RC phase shift we will use the Wien bridge oscillator. We will discuss about the Wien bridge oscillator. We will discuss about the RC phase shift oscillator. We will also discuss about the Colpitts oscillator, and we will also discuss about the Hartley oscillator. So these are all the oscillators that we are going to discuss in this course mainly, okay. So first of all, we are going to discuss about the Wien bridge oscillator. So please listen carefully about the working principle of Wien bridge oscillator, okay. So we are going to discuss about the Wien bridge oscillator. So Wien bridge oscillator, okay. So it is a feedback oscillator. Basically it is a feedback oscillator, okay. And this feedback network, you have to remember this feedback network is nothing but an RC network, and it contains two capacitors and 2 resistors in the feedback part. Okay, and you have an amplifier also. You have an amplifier also. This amplifier is in non-inverting configuration. Non-inverting configuration. Okay, it is in non-inverting configuration. And the main property of this feedback network, the feedback network is having a gain B is equal to 1 by 3 at frequency FR. So, this is the main point regarding the feedback network. So, we know that for the condition of the oscillation, one of the condition for the oscillation is the total phase shift is equal to 0, and the another condition is that the attenuation, the total the closed loop gain, that means the gain ACL, or we can say the total gain, this AV into B should be equal to 1. So, if B is equal to 1 by 3, this is into AV is equal to 1, this implies that the gain of the amplifier should be equal to 3. So, this is the very, very important point whenever we consider the Wien bridge oscillator. So, in Wien bridge oscillator, we have AV is equal to 3 and we use a non-inverting amplifier, and the B is equal to 1 by 3. You have to remember this, and we use a RC feedback network. RC feedback network. So, I am going to draw the amplifier now. You know, this is minus, this is plus, and the amplifier is having a feedback like this. This is a amplifier. So, this resistor, I will say this is R1 and this is R2, and this is the non-inverting amplifier. Now, I will draw the feedback network. This is the feedback network. Now, in the feedback network, it is a having R and a C in series. You can see it is in series, and you have we can say you have a capacitor and a resistor in parallel. So, it is very easy to remember. These are in parallel and the other two, these are in series. So, this kind of circuit you have already seen in the automatic control, and this is actually a lead lag network. A lead network is a network which is having a high pass behavior, and a lag network is a network which is having a low pass behavior. So, it is like one is having a high pass behavior and another is having a low pass behavior, so that you will be getting the overall response as a band pass response. So, this is your response of this network, and this is having a resonant frequency which is FR. Now, this let us say this is C1, C2, then this is R3 and R4, and we will be usually assuming R4 equal to R3 is equal to R, C1 is equal to C2 is equal to C, then the resonant frequency FR is equal to 1 by 2 pi RC. This is the formula for the resonant frequency. So, at resonant frequency you will get the oscillation, and what is the gain at this resonant frequency? The gain at this resonant frequency is actually the attenuation, we can say it is 1 by 3. So, this is your network, feedback network now. Okay. Now, we will connect this part as the input to the amplifier. So, this you can say as the input to the amplifier, and this is your V out, and this oscillator is known as the Wien bridge oscillator. So, when you switch on the circuit, you see here that the total gain is equal to AV into B, because what is AV? AV is equal to 3 and gain is equal to 1 by, the attenuation is equal to 1 by 3, so that it is equal to 1. But I told you that for initial startup actually we need something like this. So initial startup at these points AV into B should be greater than 1, and here AV into B is equal to 1. Now this is satisfying only this condition, AV into B is equal to 1. So initial startup, you know, when you start your car you will be giving some acceleration to make it heat, okay, to bring the car to the normal operating temperature. So like that you need some boosting here at the initial stage, though, so that then only you will get a sustained oscillation. So you will be getting a sustained oscillation. We will call this a sustained oscillations at the output. So what to do here actually at the initial stage, that we will make it that we will discuss later. But we cannot play with this circuit because this circuit is fixed one. So what we will do, we will play with the amplifier. That means at the initial startup we make AV greater than 3. So how this can be done, that we will discuss later. So before that I will discuss with you some of the formulas. So what is the formula for the voltage gain for this amplifier? So for the amplifier we know that the voltage gain is AV is equal to 1 plus RF by RI, and instead of RF we have R1 and R2. So the gain is 1 plus R1 by R2. That's it. So this is the gain. Now what is B at the frequency FR? It is equal to 1 over 3. It can be proved. That means this is your lead lag network. And this lead lag network, if you analyze it, it can be proved that it is having an attenuation of 1 by 3. Okay, 1 by 3. Now AV into B is equal to 1, but that is not enough for the starting at the initial stage. Anyway, at the resonant frequency it is given as 1 by 2 pi RC. Okay, 1 by 2 pi RC. So these are all the formulas which are related to the Wien bridge oscillator. Now we will see how we can make AV into B greater than 1 at the initial stage. So for that we will see two methods. The first method is by using the Zener diode. So by using Zener diode. So by using any of this method, by using all the methods, what you are doing, you are actually controlling the amplifier. Actually you have the amplifier, and this gain of the amplifier you are actually changing. So you are controlling the gain of the amplifier. How to control the gain of the amplifier? That's what we are going to see. Now I told you that the feedback network, anyway, I will just draw the figure, minus, plus. Now I told you one resistor and capacitor in series, then one capacitor and one resistor in parallel. This is very easy to remember. Now it is connected as a positive feedback. I told you this is positive feedback. Now for the amplifier we need a negative feedback also. Okay, and this is your network, and this is connected here. Now I told you this is your R1 and this is your R2, and the voltage gain was 1 plus RF is R1 RF by RI, which is equal to 1 plus R1 by R2, right? This is our circuit that we have seen. Am I correct? 1 plus okay, did I discussed about the voltage gain? Okay, anyway, if it is not, okay, we will see it's yeah, here we have discussed 1 plus R1 by R2. Now we see what I am going to do for the startup condition. For the startup condition, I will connect one more resistor here for the startup. If I increase this, and I will put it as R3, okay, I will put it as R3. But so what will happen to the gain? 1 plus R1 plus R3 divided by R2. Now you see the gain now increased, the gain is increased. But if I don't remove this R3, what will happen? What will happen? If I don't remove this R3, your output may go like this. It will increase, 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 and it will go like this up to infinity. So that is not a desired thing, that we don't want that condition. So what we have to do, we have to immediately remove R3 once we attain the required point. For example, you see here that initially the gain should be high. When I reach some point here, I need only steady gain. That means AV into B is equal to 1 here at these points. Okay. So I have to immediately remove R3, but manually doing all these things is impossible, because all these are happening in microseconds or milliseconds, very fast thing. So it is not possible to manually remove this. So for that, what I will do is that I will connect some new things. I will connect Zener diodes now here and one Zener diode here. Why I am connecting like this, one in one way and another in opposite way? Why I am connecting like this? Because in the oscillation actually we have positive and negative half cycle. So we need to take care of both, that's why. Now what will happen? Suppose this is your VZ1 or VZ, and this is also having the same VZ. Okay. Now when the output is positive, suppose when the output is positive, then we will see what is happening. When this is the output, basically this is output and this is plus and minus. When the output is positive, then the diode, this is Z1 and Z2, diode Z1 and Z2. When the output is positive, then the Z2 in reverse bias, and what will happen to the Z1? Z1 is in forward bias. Z1 is in forward bias. And what will happen? The current will be passing through the Zener diode. Okay, I will draw this Zener diode part again. So the current will be flowing only through the Zener diode, because Zener diodes are on now. Both of them are on. So both of them are on. So this Zener diode, both are Z. This is Z1 and Z2. Both are on. So the current will be flowing only through the Zener diode. So your resistor actually will act like an open circuit. So the resistor R3 will behave now like an open circuit. So this is the part with the resistor. So this will act like an open circuit. The current will be flowing through the Zener diode. So we can say that the current will be flowing through the Zener diode, so that the effect of R3 will not be there. So the total resistance now, this resistance is approximately, this resistance is now the resistance of the Zener diode. Okay, it's approximately, you can say it's approximately 0, you can say. So what will happen to the gain? So this is the condition when you reached the final oscillating point, okay, final point at the latest stage. So whenever the output is high, when the output is high, when the output become high, both of these Zener diodes will be on. Both the Zener diode will be on. Then what will happen? The current will be flowing through the Zener diode such that the resistance is almost 0. So the voltage gain, actually something is here, you know what is that? This is R1, as I told you. So this R1 R1 and this is R2. You have something here, this is R2 and this is your op amp anyway, minus plus, and this is your network, feedback network, and it is like this. So what is happening here, the gain is now just only 1 plus R1 by R2, and this is 3 and B is equal to 3. So AV into B is equal to 3 into 1 by 3, which is equal to 1. So there is no issue. So this is happening when the output reaches the maximum, but at the initial stage, so this is happening when at the final stage, so there is no issue. But at the initial stage, what will happen here? At the initial stage, the Zener diodes will be off. So this is happening at the final stage. So first we discussed actually final stage. Now at the initial stage, you know that we have the Zener diode. Yes. And because of this, this is R3 and this is R1 and this is your R2 and this is your feedback network, and that is our RC network, and I am not going to draw all these things. This is the RC network and this is your V out. Okay, now this is what happening here. Okay, now you see here that at initially this is Z1 and this is Z2. So at the initial stage the output will be small. So the output will be small at initial stage. So at the initial stage the output will be small. So because of the small output will leads to Z1 and Z2 will be in off state. So both will be off. That means that this part become open circuit. So what is the total resistance now? Now the current has to take the way through R3 and R1. So the total resistance become R total at the feedback, which is nothing but R1 plus R3, and Ri is same, which is R2. So the voltage gain is 1 plus Rf by Ri, that is the voltage gain is equal to 1 plus R1 plus R3 divided by R2. So you see here that there is a resistance R3. Because of that voltage gain is now high. The voltage gain increases, we can say. So at the initial stage the voltage gain is high, okay, and at the final stage the voltage gain is low. So this kind of network, actually this is nothing but the startup condition by using the Zener diode. And there is one more method also, that what we are going to discuss now. I hope that the last method is clear to you. So the startup technique using Jfet. So I will first draw the circuit diagram. It is the same circuit, please don't be confused. If you see the connections, all these are same. Okay, now you have a positive feedback, right? You have a positive feedback. So I am going to draw the amplifier in a different way. I have a positive and a negative, okay, positive and a negative, okay. Now this is positive and another one is negative. So I need an RC network. What to do with this RC network? This RC network is in positive feedback connection, okay, it is in positive feedback connection. So I will just draw like this. minus and plus. Okay. Now I will take the output from here, and I have a positive feedback. So for that I need a series RC and I need a parallel RC, right? Same thing, parallel RC. So this is a part of the feedback. This is the network. That means it is using a Jfet. Basically it is using Jfet. And I will show the main part which is controlling the gain using red color. This is Jfet circuit and it is here. Okay, so this part is actually controlling the gain of the amplifier. Now what I want to tell you is that the resonant frequency will be depending upon this RC network. So this RC network, it is 1 by 2 pi RC, which is nothing but your resonant frequency. Now how the gain is actually controlled? The gain of the amplifier is basically, it is the feedback loop. Now you see that the gain of the amplifier is you see here that this is connected here. Yeah, it is connected here to the network. Okay, it's the negative feedback. So at the negative feedback part, actually what is there in the case of feedback resistance, it is RF. RF is there. Okay, so the current is flowing through the negative feedback. So I will show the negative feedback part in red color. See the negative feedback, the current is going like this through the RF. Okay. Now what is the resistance at the input side? Because you need two resistors. One is actually RF and another is RI. And where is that RI in this picture? That's what I want to show you. That RI means this is the path to the ground. RI is actually going to the ground, right? Because here is the amplifier, minus and plus, and here is the feedback network, and this is the Wien bridge oscillator. So RF is there. Yes, you identified RF. Now where is RI? Instead of RI, you have a path to the ground. Actually RI is a path to the ground, but RI is going through the Jfet. RI is going through the Jfet and through R3 to the ground. So what is your RI? Instead of RI, you have R3 plus RF. Sorry, not RF, R3 plus the resistance of the Jfet. The resistance of the Jfet. The resistance of the Jfet is RDS. You know what is Jfet? Having drain and the source. So the resistance between drain and the source is RDS or R-ds. R-ds. So you see here that your RI is R3 plus R-ds and RF is actually RF itself. So your RF is just RF itself and your RI is nothing but R3 plus R-ds. So what is your voltage gain? It is 1 plus RF is RF itself, then RI is R3 plus R-ds. So this is your gain actually. This is your gain. Now, but how actually if R-ds is equal to 0, if R-ds is equal to 0, if there is no resistance or if the Jfet is conducting fully, that means if R-ds is equal to 0, then what will be the gain? AV is equal to 1 plus RF by R3. So if R-ds is equal to 0, then the gain will be high, right? The gain will be high if R-ds is equal to 0. Why it is high? Because there is no R-ds. And this case, when this case appears, the gain is low. So we have two things for the gain. Either if R dash ds is equal to 0, the gain is equal to 1 plus Rf by R3. If R dash ds is not equal to 0, we have gain is equal to 1 plus Rf by R3 plus R dash ds. So this gain actually it is low and this gain it is high. Okay, so the first gain is actually high and the second gain is actually low. But when all these conditions will appear, that is what we are going to see. So before that, we need to know what is the property of the Jfet. You know that this is your VGS and this is your ID. You have seen this property of the Jfet like this. So when VGS become VGS off, okay, this is 0 volt. So when VGS become VGS off, then ID is equal to 0. So ID is the drain current, ID equal to 0 when VGS is equal to VGS off, and it is a negative voltage because you see this is the positive axis I have drawn here, and channel Jfet actually it is negative voltage. Now what is the maximum current? The maximum current you are getting at IDSS. At IDSS, what is your VGS? Actually VGS is equal to 0. So VGS is equal to 0 at IDSS. So please remember two things. ID will be equal to 0 when VGS is equal to VGS off, and ID is equal to IDSS or maximum when VGS is equal to 0. So if you give VGS as 0, ID is maximum. ID is maximum means that your resistance, whenever the current is maximum, the resistance is minimum. That means that our RDS is approximately 0 or very small. Now in this, so this is the situation here, okay, in this case. So what about when ID is equal to 0, when the drain current is equal to 0, the drain current will be equal to 0 means that ID is equal to 0. In this condition, ID is equal to 0, it means that the resistance is maximum. That means R dash ds is maximum. That is maximum. That means you have some R dash dx. So this is the condition. Now we will see the working of this. Okay. Now we will see the working of this particular circuit. You can see there is a diode which is connected at the output. So this is the diode, and there is a RC network here. You can see there is an RC network here. Now whenever the output at the initial stage, the output will be very small. The output will be very small. So at the initial stage, the working principle, I am just saying working. So at the initial stage, output will be small, right? If the output is small, the diode will be in off state. The diode will not be conducting. The diode will not be conducting. So if the diode is not conducting, the capacitor C3 will not charge, right? If the diode is not conducting, that implies that C3 will not charge. So the voltage across C3 is approximately 0, small, right? It is also small. Since it is small, it is connected. This is the gate and this is the source. You can see here that this is VGS. So VGS also will be small, right? So VGS is approximately 0. But when VGS is approximately 0, then I told you when VGS is equal to 0, the current will be maximum. That means the drain current will be maximum. Then ID is equal to IDSS, which implies that your resistance, I have told you, when the current is maximum, the resistance is minimum, your R dash ds is approximately 0. If R dash ds is approximately 0, then the voltage gain is 1 plus Rf by R3, Rf by R3, 1 plus Rf by R3. So the gain will be maximum. Then the gain will be maximum. So then the gain will be maximum, that means gain will be high, you can say. When the gain is high, AV into B will be greater than 1. That's it. So when AV into B is greater than 1, then what will happen? If AV into B is greater than 1, automatically the output will start increasing. So the output will start increasing. When the output start increasing. So when the output increases, what will happen? So I will just write it. When AV into B is greater than 1, then what will happen to the output? The output will increase like this. So when the output increases, when output reaches a high value or a particular threshold, when the output reaches a particular threshold, then what will happen? It will slowly charge the capacitor, right? The negative cycle, that means the output may be positive or negative, but only during the negative cycle, because you see this is the n-type semiconductor and this is the p-type semiconductor of the diode. So this is the cathode and one is the cathode and another is the anode. So when the output become negative, it will actually the diode become on. So the diode become on when the output is negative. When the output is negative, the current will be flowing from the ground to the negative potential, towards the negative potential through the diode. So what will happen? The capacitor will be charging like this. So when the output reaches a particular value, that means when the output become high, the negative cycles of the output will charge the capacitor as shown. So the negative cycle, then the negative cycles of the output will charge the capacitor. So how it is charging? This is the capacitor and this is the diode, as I have told you. So this is the ground, so it will charge like this during the negative cycles. So if the capacitor charge like this, this become positive and this become negative. So you are actually now getting a voltage between, and here is there is a resistor here, because why you are connecting a resistor? If you don't connect the resistor, the capacitor sometimes will the capacitor will discharge immediately. So you have to maintain some voltage across the capacitor. Okay, if you don't connect the resistor, the capacitor will charge towards very high voltage. That also a problem. Okay, now this is your Jfet here. So this is your gate. So the voltage VGS, it will charge the capacitor. So because of that, the VGS will be, VGS was 0 previously, now VGS is negative. VGS is negative now, and this charge will increase, so that the magnitude of VGS will also increase. The magnitude of the VGS will increase. So as the magnitude of the VGS increases, I told you, and when VGS reaches VGS off, that means this is the characteristics of the Jfet. I told you this is the characteristics of the Jfet. This is IDSS and this is ID, and this is your VGS. When it reaches VGS off, that means this is negative, it is negative. When it reaches VGS off, when VGS is equal to VGS off, because of the charging of the capacitor is having voltage plus minus now, like this. So it is having voltage as shown like this. So this is your gate, and here it's come around the voltage, so its VGS will be almost here, and because of this reason, whenever it reaches VGS off, or you can say when VGS increases, when magnitude of the VGS increases, then this will lead to the decrease in the current. That means you see when it reaches here, the current is decreasing. So the drain current will decrease. That means that the resistance R dash ds is increasing. So if R dash ds is increasing, or it reaches having a value R dash ds, then the voltage gain is 1 plus Rf by, what is that resistance? It is R3. So 1 plus Rf by R3 plus R dash ds. Okay. So this is what happening. So what is happening? The gain is now reduced. So as you reach a particular level of the voltage, actually the gain is now reduced. Now you can see AV into B is maintained, and it will be maintained to 1. So this is what happening. So I will explain with the circuit diagram again. So initially actually this capacitor is having a voltage, the voltage across the capacitor was 0. So then what happens? The Jfet is having VGS is approximately 0. When VGS is 0, your R dash ds is actually approximately, it is also minimum, it is approximately 0, because the current will be maximum. IDSS is or the current will be maximum, ID will be maximum. When VGS is 0, ID is maximum. Okay. Now because of that, if R dash ds is 0, then the gain will be high. Because of that I have shown you, the gain is high. That's what I have shown here. The gain is 1 plus Rf by R3, because there is no R dash ds. So the gain is high. So what will happen? The output automatically increases. Output increases. When the output increases, what will happen? Slowly this diode will become conducting. So during the negative half cycles of the output, during the negative outputs, the capacitor will be actually the current will be flowing through the capacitor as shown like this, through the diode, through this diode. So what will happen? The capacitor will be charging. When the capacitor charges, then when the capacitor charges, what will happen? Then the VGS will increase. Then the VGS will increase. VGS increases. When VGS increases, the current through the Jfet will be reducing. The current through the Jfet will be reducing, or we can say that R dash ds will be increasing. When R dash ds increases, this R dash ds and R3 are in series, both are in series. Because of that, actually the gain is having a formula, actually 1 plus Rf by Ri, and Ri is nothing but your R3 plus R dash ds. So what will happen? Your gain is now low. So whenever the output reaches high, the gain automatically comes down. So that what will happen? The gain will now maintain AV into B is equal to 1. How we can adjust all these things? That's why we are using a potentiometer. It's very difficult to control precisely. So if you want a good oscillation, you have to control this gain by using RF. So you can control the gain control mechanism by using RF, and this is the automatic startup. So by using a Jfet and a diode and RC network, you can actually create a startup, and also by using Zener diode you can create a startup. So this is nothing but the startup condition for the Wien bridge oscillator. Okay. So I hope this is clear to you. Now we have I will discuss one more type of oscillator, which is nothing but the RC phase shift oscillator. RC phase shift oscillator. So RC phase shift oscillator. This is also a feedback oscillator. Okay, this is the second type that we are discussing, feedback oscillator, and the feedback network make use of RC network. Okay, RC network as the feedback. Now there will be 3 capacitors and 3 resistance in RC feedback. Okay, in RC feedback, and we will use an amplifier which is a inverting amplifier. That's a difference. Inverting amplifier. So you know that the inverting amplifier, we will use an inverting amplifier. In inverting amplifier, if you give positive, you will get negative, right? Now you have the feedback network. I told you the total phase shift should be equal to 0 degrees. So this is positive, input is giving. If your input is positive, you will get a negative, that means it is 180 degree. So you have the feedback network, it also should provide 180 degree, then it becomes 360. So total phase shift become 180 plus 180. So this become 360 degree or equivalent to 0. So you can take the output right here. So if you give a negative here, you will get again positive here. So that's why it is providing 180 degree out of phase. And this 180 degree out of phase is provided by 3 RC network. Okay, because each RC network here in this case will provide a phase shift around 60 degrees. Okay, that's how you are going to design it. Now we will see the circuit diagram. You have an inverting amplifier, so the non-inverting terminal will be grounded, and I told you this is your R, F, and this is. Now you need something, the RC network here. So what is that RC network? You have one capacitor C1 and R1, RC network, one RC network. The second one C2 and R2, the third one C3 and R3. Okay, now this is V out, and this R3 that is not ended here because you need a feedback, a negative feedback. That's why through this R3 you are connecting here. So this is the RC phase shift or RC feedback oscillator. Okay, now the resonant frequency, if all the resistors are equal, if R1 equal to R2 equal to R3, okay, then the resonant frequency is given as 1 by 2 pi square root of 6 into RC. Okay, so this is the formula for finding the resonant frequency. That means it is acting as a band pass filtering, it is acting as a phase shift network, and the resonant frequency is 1 by 2 pi root 6 into RC. And this is the feedback part. Actually, this is the feedback part of the network. This is actually showing the feedback network, and this is having the gain B is equal to 1 by 29. So the gain of the amplifier should be, this is the amplifier part, the gain of the amplifier should be, AV should be equal to 29, then only AV into B is equal to 1, right? So initial startup, you can use any method like as we have discussed before, but you see here that we see the condition AV is equal to 29 and B is equal to 1 by 29, so that we will be getting AV into B as 1. So what is happening here? Actually, suppose you have when you switch on the circuit, you will be having a small output, and this small output will be reaching here, and finally you will be getting get amplified 29 times. So you will be getting a large output, and it is will be out of phase. Suppose if you give positive here and you will be getting then negative here. Okay. Now because of the phase shift you will be getting opposite phase again. So I will just show here, if you give positive and negative then you will be getting negative and positive, but again at the end of this circuit you will be getting positive and negative, then it will be again fed back here and amplified, and then it is going through the frequency selective network, and finally you will be getting the output, and the working principle is almost the same. Okay, and here we are using non-inverting amplifier and 3 RC network for getting a total phase shift of 360 degree. So the amplifier is providing a phase shift of 180 degrees and your feedback network is providing a phase shift of 180 degree, so that you will be getting 360 degrees. So we will see a problem, after that we will wind up. So the problem so for the exam I will be asking design problems also. Okay, so in design problems you have to sketch the oscillator and find all the parameters. So this is RF, this is C1, this is R1, this is 10 kilo, and this is 0.001 microfarad. Again second RC network, this is R2 and C2, third RC network C3, and this is R3, and this is again R3 is connected in feedback. Okay, this is 10 kilo ohm and this is 10 kilo ohm. Okay, now this is 0.001 and this is equal to 0.001 microfarad, 1 microfarad, or 0.001. Okay, you have to find, obtain, this is a problem, so obtain the RF and obtain the frequency of oscillation, So if you connect the circuit like this, it will provide the oscillation. Now how to find the RF? So what is the, this is a which amplifier? The gain, the amplifier is the type of, this is the answer. So the amplifier used is inverting amplifier. So the gain of the inverting amplifier is minus RF by RI. It is minus of RF. And where is your RI? You see here, this guy actually act as the RI. So this will act as the RI. So it is divided by R3. Okay. Now we want to find R3. So R3 is given. So we need to find what is RF. So RF is equal to 29 times R3, which is equal to 29 into 10 kilo ohm, which is equal to 290 kilo ohm. Okay. So the magnitude of the gain, I can say it is 29. The magnitude of the gain. Okay, it's like magnitude of the gain. So the AV is minus 29, or magnitude of the gain is 29. We can say. So you see, it is 290. We got 290. Okay, 29 into R3, because the gain for RC phase shift oscillator is always minus 29. Okay. Now what is the, so this is the first part that's finished, part A. Now the second part is the resonant frequency. It is 1 by 2 pi root of 6 into R into C. Okay. So this is given as 1 by 2 pi root of 6 into RC 10 kilo ohm multiplied with 0.001 microfarad, and this you will get it as 6.5 kilohertz. Okay. So we will so this is how you can solve this kind of problems. Now we will see design problems later in the next class. I hope all of you understood how the oscillator is working and what is the basic principle behind it. And the oscillators are having many application, especially in the communication systems. So the applications include especially in the communication systems, okay, and also in many electrical systems, other electrical systems, okay. Oscillators are having lot of applications in communication system. You cannot imagine a communication system without an oscillator, okay. I hope everything is clear to you. Inshallah, we will discuss, we will continue in the next lecture, okay.